Fine, let's start. Number 1. The L-salt Neanderthal feces. There is no object to look at. What survives is a stain of molecules soaked into 50,000-year-old dirt beside the remains of a fire in a rock shelter near the town of Alcoy in the Alicante province of eastern Spain. The site is called El Salt. It has been excavated systematically since 1986, and the relevant deposit is a layer archaeologists label Stratigraphic Unit 10. In 2014, a doctoral student named Ainara Sistiaga, working at the University of La Laguna in Tenerife, published a paper in the journal PLOS One announcing that this sediment held the oldest identified excrement from the human lineage. The chemistry is worth understanding because it is what makes the claim possible. Your gut bacteria take cholesterol and convert it into a molecule called coprostanol. Nothing else produces it in quantity. Find coprostanol in soil, and you have found the remains of a mammal's digestive tract. Those same bacteria perform the same trick on plant sterols, producing a compound called 5-beta-stigmastanol. So the sediment carries two signals at once. One says animal food passed through this gut. The other says plant food did. The ratio between them is the actual measurement, and it is the ratio that separates a carnivore from an herbivore from something in between. Sistiaga's team, which included Carolina Malol, Bertila Galvan, and the organic geochemist Roger Summons of the Massachusetts Institute of Technology, took 5 samples. All 5 were positive. One peaked at around 73 micrograms per gram. For 2 decades, the dominant reconstruction of the Neanderthal diet came from nitrogen isotope ratios measured in bone collagen, in work by researchers including Hervé Bocheron and Michael Richards. Those measurements placed Neanderthals at the same trophic level as hyenas and wolves. Collagen is protein, and it preferentially records the protein a person ate. Vegetables barely register, so the isotopes were answering a narrower question than everyone assumed. The L-salt chemistry filled in the gap. Meat still dominated, but plants were routine rather than occasional. And because the deposit sits directly beside a hearth, in sediment that Malol has studied by lifting intact blocks and impregnating them with resin, there is a behavioral reading as well. Somebody was using the edge of a living space as a latrine. 3 explanations remain live. The mainstream one accepts the Neanderthal attribution outright. A cautious reading points out that sterols can drift downward through sediment with groundwater. A third suggests some plant molecules came from bedding, from medicine, or from the stomach contents of the animals being eaten. All of it survives for one reason. These are fats. They do not dissolve in water, and they were sealed into mineral sediment where microbes could not reach them. Number 2. The Heslington Brain. In August of 2008, an excavation was running on farmland at Heslington East, just outside York in England, clearing ground ahead of a University of York campus expansion. York Archaeological Trust was in charge. A finds officer named Rachel Cubitt was cleaning soil off a recovered skull when she felt something shift inside the cranium. What was in there should not have been there. It was a shrunken, yellowish, firm mass, and it had folds and grooves still visible on its surface. Those folds are the gyri and sulci of a human brain. It had lost roughly 80% of its original volume, and it had kept its shape. Consider why this is close to impossible. The brain destroys itself faster than any other organ after death, digested within days by its own enzymes in a process called autolysis. Under normal burial conditions, nothing is left within a fortnight. Yet radiocarbon dating placed this man between roughly 673 and 482 before the Common Era, in the British Iron Age. He was 30 to 45 years old, judged from tooth wear and the closure of his cranial sutures, and only his head was recovered. The skull came with the mandible and 2 neck vertebrae, and those vertebrae carry cut marks from a blade. There is trauma around the hyoid region, suggesting he was hanged or strangled first, and then decapitated. Sonia O'Connor, a conservator and archaeological scientist at the University of Bradford, led the first investigation, and she was well placed for it, having already catalogued dozens of preserved brains sitting unrecognized in museum stores. The biochemistry took longer. Axel Petzold, a neurologist at University College London, ran a study spanning roughly a decade, published in 2020 in the Journal of the Royal Society Interface. His team found neurofilaments and glial fibrillary acidic protein still present and still folded into tight aggregates, resistant to the enzymes that should have dismantled them. Something released shortly after death appears to have locked those proteins into a form that could not be broken down, which means the aggregation may itself be the preservative. The setting cooperated. The head was placed in a pit dug into wet, fine clay, cold and waterlogged, and effectively without oxygen within hours. No tannins, no embalming compounds, and no heavy metals turned up in testing, so nothing artificial was involved. 3 readings compete. One says this was a rare natural convergence of speed, cold, and water. One says the protein chemistry did the work by itself. One notes that an isolated head, deliberately buried, belongs alongside the other Iron Age head deposits of Northern Europe, and treats this as a killing with ritual meaning. Petzold's interest is partly clinical, because protein aggregates of this kind drive neurodegenerative disease, and here is one that has held together for 2,600 years. A survey led by Alexandra Morton Hayward at Oxford in 2024 counted roughly 4,000 preserved ancient brains worldwide. Number 3. The Saqqara Embalming Workshop. Preservation at Heslington was an accident. In Egypt, it was an industry, and in 2018, archaeologists found the factory floor. The site is Saqqara, the necropolis serving ancient Memphis, about 30 kilometers south of Cairo. A joint Egyptian and German mission, directed by Ramadan Hussein of the University of Tübingen, cleared a shaft roughly 30 meters deep and found a rectangular chamber cut into bedrock at the bottom. Inside was a stone slab for laying out a body, channels cut into the floor for drainage, a large incense burner, and a shaft for ritual waste. Hussein died in 2022, before the chemistry that made the site famous was published. More than 120 ceramic cups and bowls were recovered, and many of them are inscribed. The inscriptions are not decorative. They name a substance and then give an instruction. Translated, they say things like to put on his head, or to wash, or to make his odor pleasant. That is an operating manual distributed across the containers of the workshop, dating to the 26th dynasty, roughly 664 to 525 before the Common Era. In February of 2023, Maxime Rajot of Tübingen and Philipp Stockhammer of the Ludwig Maximilian University of Munich published the residue analysis in the journal Nature. They scraped 31 vessels and ran the residues through gas chromatography with mass spectrometry. Animal fat, beeswax, bitumen, castor oil, juniper and cypress tar, cedar oil, plant gums. Then 2 entries that changed the geography of the trade. Dammer comes from the rainforests of Southeast Asia, and Elemi from the tropics of Southeast Asia, or Africa, which means the embalming workshops of Memphis were being supplied through trade networks reaching across the Indian Ocean. The labels rewrote vocabulary too. Egyptologists had translated the word antiu as myrrh or incense for over a century. The chemistry indicates it named a mixture rather than a single gum. The word safet turned out to designate a scented fat preparation. Applications were specific rather than general, with coniferous products directed at the head and fats and beeswax used for wrapping the body and sealing the abdominal cavity. And the recipe works. Pistacia and conifer resins genuinely inhibit bacteria and fungi, so this was pharmacology as much as ritual. The same complex produced the mummy of a woman named Didi Bastet, whose internal organs had been treated in an unusual way, and a mummy wearing a gilded silver mask, a priest serving the goddesses Mut and Neutches. Interpretations differ on the details. The mainstream reading treats the vessels as working stock from a commercial operation serving local elites. A philological objection warns that some labels are ritual designations and should not be mapped one-to-one onto chemical compounds. A skeptical reading suggests the Asian resins passed through many hands and have been overread as evidence of direct contact. Number 4. The Norje Sunnansund fermented fish pits. Egypt was preserving bodies. In southern Sweden, 9,200 years ago, people were doing something that sounds worse and turns out to be cleverer. The site is Norje Sunnansund, near Sölvesborg in Blekinge, excavated between 2010 and 2012 ahead of road construction. Adam Boethius, an osteoarchaeologist at Lund University, published the analysis in the Journal of Archaeological Science in 2016. What he described was a trench roughly 9.5 meters long and up to 1.5 meters wide, lined with pine bark and packed with fish. The estimate runs to about 60,000 individuals, drawn from a site that yielded over 200,000 bone fragments in total. Most of them are freshwater roach, with perch and pike alongside. None of it had been cooked. Heat alters bone surfaces in ways that are easy to recognize, and these surfaces are unaltered. Instead, the bone shows acid etching, the kind produced when lactic acid generated by bacteria dissolves a skeleton slowly from the inside. That is fermentation. The construction supports the reading. Bark lining and a probable covering of skins sealed the trench from air, which is what fermentation requires. And residues of wild boar fat and seal fat suggest a sealing and enriching layer laid over the top. The whole assembly sat in cold, wet ground, which functioned as a cellar and held the temperature stable through a Scandinavian winter. The fish were gutted and layered whole. The technique is a direct ancestor of Swedish surströmming and Icelandic hakkarl, both of which are still made and still divide opinion violently. The scale is the part that matters scientifically. 60,000 fish is a surplus, produced deliberately and held for later, and that behavior has a name in economic anthropology. Delayed return storage means investing labor now for a payoff months away, and for most of the 20th century, it was treated as a marker of agricultural societies. Hunter-gatherers were assumed to consume what they caught and move on. Boethius argued that this pit pushes evidence for sedentism in southern Scandinavia thousands of years earlier than the standard model allowed, and the site also produced the region's earliest evidence for a settlement occupied across seasons rather than visited briefly. The mainstream reading takes the fermentation as deliberate and the organization as semi-sedentary. A skeptical reading suggests the acid signature could come from post-depositional soil chemistry, making the deposit ordinary refuse. A third reading proposes the fish were processed for oil and fat rather than flesh, with fermentation as a side effect of the method. The nutritional logic has not changed in 9,000 years. Fermentation preserves protein and increases the availability of certain vitamins, and it does all of this without fuel, without salt, and without the reliable dry weather that drying fish demands. Number 5. Lola and the Syltholm chewing gum. That pit fed a settlement. The next object is small enough to sit between two fingertips, and it contained an entire human being. During excavation for the Fehmarn Belt Tunnel link, at a site called Syltholm on the Danish island of Lolland, archaeologists recovered a chewed lump of birch bark pitch. It is roughly 5,700 years old, from the very beginning of the Neolithic transition in Denmark. In December of 2019, a team led by Theis Jensen with Hannes Schroeder as senior author, both at the University of Copenhagen, published what they had pulled out of it in Nature Communications. They had recovered a complete ancient human genome. There were no bones anywhere in the excavation. There was only spit. You heat birch bark in a container with very little oxygen until tar sweats out of it, a controlled pyrolysis that hominins were performing in the Middle Pleistocene. It sets hard and worked as the glue that fixed stone points to wooden shafts. To work it, you chew it, because body heat and saliva soften it. It may also have been chewed for its mild antiseptic properties. What that chewing does, in preservation terms, is remarkable. It seals human cells and everything else in the mouth inside a water-repelling antimicrobial matrix, and then the whole lump gets spat into a wet coastal landscape that is later sealed under marine sediment without air. The chewer was female, and the team nicknamed her Lola after the island. Her genome indicates dark skin, dark hair, and blue eyes, the combination characteristic of Western hunter-gatherers rather than the incoming Anatolian farmers who were spreading into Europe around the same period. Her ancestry is continental hunter-gatherer rather than Central Scandinavian. She carried the genetic variant for lactase non-persistence, so she could not digest fresh milk as an adult. Then the analysis went further than her own cells. The pitch preserved her oral microbiome, including Porphyromonas gingivalis and Treponema denticola, both organisms associated with periodontal disease. It preserved Epstein-Barr virus DNA, among the oldest instances yet recovered of the virus that causes glandular fever. It preserved Streptococcus pneumonia, evidence of respiratory bacterial carriage in a Neolithic person, and it preserved her last meal, or something close to it, in the form of hazelnut and mallard duck DNA. The mainstream reading treats all of this as an accurate snapshot of one individual at one moment. A cautious reading points out that some microbial DNA could be environmental, from the burial matrix rather than the mouth. A third reading argues the chewing may have been purely technical tool work with no consumption intended at all. The method has since spread. Chewed pitch from Huseby Cleve in Sweden, roughly 10,000 years old, has yielded partial genomes by the same route. Number 6. The Cheese of Ptahmes. Lola's find was accidental. The next one was placed in a tomb on purpose, as food for the dead, and it was already dangerous when it went into the ground. Ptahmes was mayor of Memphis and overseer of the treasury, serving under the pharaohs Seti I and Rameses II in the 13th century, before the Common Era. His tomb at Saqqara was located in the 1880s, then lost again beneath drifting sand for more than a century. A Cairo University mission under Ola El Aguizi rediscovered it in 2010, and in 2013 and 2014 excavators recovered a broken storage jar. Inside was a solidified whitish mass, with fragments of canvas fabric still stuck to it from the covering that had been laid over the jar's mouth. Enrico Greco of the University of Catania led the analysis, published in the journal Analytical Chemistry in July of 2018. The technique was proteomics. You dissolve the sample, chop its surviving proteins into short fragments called peptides, and then identify those peptides by running them through liquid chromatography coupled to tandem mass spectrometry. Different animals produce slightly different versions of the same milk proteins, so the peptide sequences act as a species signature. The result identified cow milk together with sheep or goat milk, or a blend of the two. Certain whey proteins were absent, which is what you expect in a solid aged product rather than a fresh curd or liquid. That makes this the oldest solid cheese ever identified, and the breathable canvas covering is exactly how you store something meant to age. The peptide data included markers from Brucella melitensis, the bacterium responsible for brucellosis. In humans, that infection produces recurring fever, joint pain, and drenching night sweats, and it can settle permanently into bone or heart tissue. The identification is plausible rather than exotic, because unpasteurized sheep and goat dairy remains the principal route of human brucellosis infection today. It also pushed the disease back in time, becoming the earliest direct biomolecular evidence of brucellosis, ahead of the skeletal indications archaeologists had previously relied on. Egyptian dairying was already documented in tomb paintings, in vessel residues, and in written records, but almost never in surviving product. Preservation came down to environment. The desert is alkaline, extremely dry, and burial under sand shut down microbial degradation almost entirely. The mainstream reading is straightforward. An aged mixed milk cheese deposited as a grave good and contaminated before burial. A skeptical reading notes that Brucella peptides overlap with those of related organisms, making species-level identification from degraded material risky. A third reading suggests the mass might be a ritual or cosmetic fat preparation rather than food, since unguents also appear in tombs. If the food reading holds, it tells you something quietly important about grave goods. They were real, and they were meant to be eaten. Number 7. Mumia and Mummy Brown. Egypt buried its dead with food. Europe, centuries later, dug up Egypt's dead and swallowed them. The story starts with a translation error. The word mumia comes from the Persian word mum, meaning wax, and it originally referred to bitumen that seeped out of mountains in Persia and was prized as a medicine for wounds and bruising. Egyptian bodies treated with dark resins looked to observers unfamiliar with the process as though they were full of the same black substance. The name transferred from the mineral to the corpse. By the 12th century, the Baghdadi physician Abd al-Latif was recording mummy being sold and consumed as medicine in Egypt. By the 16th century, a full European trade ran out of Alexandria and Cairo through apothecary shops across the continent in powdered human remains. Demand outran supply. In 1564, the French physician Guy de la Fontaine traveled to Alexandria to inspect the trade at its source and found a dealer manufacturing mummy from the recently dead, using slaves, executed criminals, and plague victims dried in the sun. The English merchant John Sanderson recorded shipping around 600 pounds of mummy to England in 1586. The surgeon Ambroise Paré wrote against the practice, arguing it caused vomiting and foul breath and did nothing whatsoever for the bruising it was sold to treat. But the underlying idea was mainstream medicine, not a fringe curiosity. Powdered skull, skull moss, human fat, and distilled blood all appear in respectable European pharmacopoeias, and Charles II of England reportedly paid for and drank a preparation of distilled human skull known as the King's Drops. The trade then made a second career for itself in art. Ground mummified flesh and bone, mixed with white pitch and myrrh, produced a pigment called mummy brown, sometimes sold as caput mortuum. It was a transparent, rich, glazing brown that sat tonally between burnt umber and raw umber. Eugène Delacroix and Martin Drolling are among the documented and alleged users, along with painters in the pre-Raphaelite circle. Edward Burne-Jones, when he learned what was actually in the tube, carried it into his garden and buried it, a scene his wife Georgiana recorded. The London colormen C. Robertson and Company kept selling the pigment into the 20th century, and told Time magazine in 1964 that they had simply run out of mummies. Conservation scientists struggle to confirm its presence in specific paintings, because once degraded, its components resemble ordinary earth pigments. The mainstream account treats this as a documented trade built on a mistranslation and sustained by demand. A revisionist account stresses that much of the product was never Egyptian at all, meaning the trade consumed contemporary corpses under a false label. A cultural reading points out that corpse medicine followed a coherent early modern theory in which vital spirit persisted in the body. It ended not through ethics, but through exhausted supply and synthetic replacements. Number 8. Bog butter. Europe consumed what it dug up. Ireland did the reverse and buried its food on purpose. Bog butter is the term for lumps of dairy fat or rendered animal tallow deliberately placed in peat bogs across Ireland and Scotland. Over 500 examples have been recorded in Ireland alone, and the National Museum of Ireland holds a substantial reference collection of them. The radiocarbon dates span an enormous range, from roughly 3,500 years ago in the Bronze Age through to the 18th century. In 2009, a find at Ballard Bog in County Offaly weighed around 45 kilograms and came out of the ground inside a wooden keg. In 2016, a lump from Embalming Bog in County Meath weighed about 10 kilograms, dated to roughly 2,000 years old, and was reported by the man who found it as still smelling powerfully of dairy. Containers vary enormously. Some lumps sit inside wooden kegs or baskets, some are wrapped in bark, some are packed into animal bladders and skins, and some were simply pressed into the peat with nothing around them at all. Burial depth is typically 2 to 5 meters, well below the water table. A bog offers 4 preservation properties at once. It is cold. It is almost entirely without oxygen. It is acidic. And sphagnum moss releases compounds that actively inhibit bacterial growth. Under those conditions, butter does not rot. It converts. Over centuries, it shifts toward a waxy mass dominated by saturated fatty acids, which in composition and appearance closely resembles adipose hair, the grave wax that forms on human bodies in the same environment. Gas chromatography combined with compound-specific stable isotope analysis, a method developed for archaeological lipids by Richard Evershed at the University of Bristol, measures carbon isotope ratios inside individual fatty acids, which separates dairy fat from the carcass fat of ruminant animals. Applied to Irish specimens, it indicates most really are butter, with a meaningful minority being rendered meat fat. Why anyone did this remains genuinely open. The practical explanation treats the bog as a cold, anaerobic larder, storing a valuable commodity that medieval Irish law tracts confirm was used as stored wealth and paid as tribute. The ritual explanation notes that bogs sit on boundaries between territories, and that the same bogs received weapons, ornaments, and human bodies as offerings. The culinary explanation argues the burial was deliberate aging, a controlled fermentation intended to develop flavor, and Irish chefs have since revived bog aging on exactly that theory. The three are not mutually exclusive, and across 3,000 years, the practice almost certainly served different purposes at different times. Finders who have tasted recovered lumps describe something between strong cheese and paraffin. Number 9. Ancient dental calculus. Bogs preserve by accident of chemistry. The next archive was cemented to the inside of people's mouths while they were alive. Dental calculus is plaque that is mineralized. A living film of bacteria on the tooth surface takes up calcium phosphate from saliva and hardens into a crust, and it does this in successive layers throughout a person's life. Every layer traps whatever was in the mouth at the time: bacteria, food debris, starch granules, pollen, textile fibers, inhaled soot, pigment particles. It is a rock forming on a tooth with a biological record inside it, and for most of the 20th century, archaeologists scraped it off during routine skeletal cleaning and threw it away as dirt. Christina Warrener, now at Harvard University and the Max Planck Institute, led the work that reversed that. Her landmark study, published in Nature Genetics in 2014, analyzed calculus from a medieval cemetery at Dalheim in Germany and recovered a complete oral microbiome, the pathogens responsible for periodontal disease, and antibiotic resistance genes existing centuries before antibiotics were invented. Matthew Collins, working between Copenhagen and Cambridge, has described calculus as the richest single source of ancient biomolecules anywhere in the archaeological record. A whey protein called beta-lactoglobulin survives in calculus, giving direct evidence that a specific individual drank milk, independent of anything a pottery residue might suggest. Starch granules survive too, identifiable to plant family, revealing grains, tubers, and legumes that leave no other trace of themselves at all. Then there are the findings nobody predicted. In 2019, a study in Science Advances, led by Anita Radini, with Warrener as senior author, found particles of lapis lazuli embedded in the calculus of a medieval German woman. Lapis was ground to make ultramarine, a pigment then more valuable than gold, And the most likely route into her mouth is that she was a manuscript illuminator who shaped her brush tip with her lips. Neanderthal calculus has been equally productive. Work led by Laura Weyrich, published in Nature in 2017, examining material from Spy Cave in Belgium and other sites, found dramatically different diets between populations, and recovered a near-complete genome of an oral microbe called Methanobrevibacter oralis at around 48,000 years old. The mainstream reading treats calculus as a faithful sealed record of what entered the mouth. A cautious reading warns that a trapped particle may record environmental exposure rather than a meal. A third reading notes that heavy calculus formation is partly genetic and partly dietary, so the people best represented in this archive are a biased sample of the population. Contamination is the constant methodological threat, since handling and burial soil can overwhelm the original signal. Calculus survives on teeth in almost every skeletal collection on Earth, and comparing ancient with modern mouths shows a measurable collapse in oral microbial diversity after industrialization. Number 10. The Lloyds Bank Coprolite. Everything so far has been recovered from inside people. This is what came out. In 1972, work on a new Lloyds Bank branch on pavement in York, England, turned up a single intact human stool from the 9th century of the Common Era. The same waterlogged deposits were excavated on a far larger scale a few years later at neighboring Coppergate between 1976 and 1981, revealing the Viking Age town of Jorvik beneath the modern street. It is roughly 20 centimeters long and 5 centimeters wide, which makes it the largest preserved human stool on record anywhere in the world. It survived for the same reason the leather, textiles, and timber at Coppergate survived. The organic deposits of York are waterlogged and starved of oxygen, and in those conditions, material that would normally vanish within weeks simply sits there. Andrew Jones, a paleoscatologist working for York Archaeological Trust, carried out the analysis. The contents are dense with bran and cereal husk, indicating a diet built on coarse bread and grain with very little vegetable matter alongside it. There were also several hundred parasite eggs, principally whipworm and mawsworm, meaning the man who produced it was carrying a chronic intestinal parasite load that would have been entirely unremarkable in a city with no sanitation. In 1991, Jones remarked that the specimen was as valuable in its field as the crown jewels are in theirs, and attached an insurance figure of around $39,000, which made a piece of Viking excrement internationally famous. It is displayed at the Jorvik Viking Center, which opened in 1984 on the Coppergate site, and in 2003 a visiting party dropped it and broke it into 3 pieces. Conservators reassembled it and put it back. Viking York is history rather than prehistory, so this specimen is the recognition anchor rather than the deepest example. Human paleofeces preserve diet, parasites, gut microbiome, and pathogen DNA together in one deposit, which no other material does. At the Paisley Caves in Oregon, paleofeces dated to roughly 14,300 years before present, carried human mitochondrial DNA, and became central to the argument that people were in the Americas before the Clovis culture. Hines Cave in Texas has produced thousands of desiccated human paleofeces spanning millennia of dietary change. In 2021, a study led by Marcia Wibowo and Alexander Kostic reconstructed nearly 500 ancient gut microbial genomes from paleofeces and found a substantially more diverse microbiome than any modern industrialized population carries. The mainstream reading of the York specimen treats it as ordinary for its time and place. A cautious reading points out that one stool represents one meal cycle from one person. A taphonomic reading suggests some large specimens are composite cesspit deposits rather than single events, which would change the dietary interpretation entirely. Step back from the individual finds and a pattern appears. The real protagonist of every story in this video is preservation chemistry, and it operates through only a handful of roots. The first is anoxia. Remove oxygen and aerobic bacteria stop working, which is what saved the Heslington Brain, the Syltholm pitch, and the York Coprolite. The second is desiccation. Remove water, and nothing microbial functions at all, which is what saved the Cheese of Ptahmes under Egyptian sand. The third is acidity, combined with the polyphenols that sphagnum moss releases, which is the bog mechanism that preserves butter and bodies by identical means. The fourth is mineralization, where a biological deposit turns into rock, which is what dental calculus does while a person is still alive. There is a hierarchy inside all of this. Lipids survive best because fats are chemically stable and do not dissolve in water. Proteins come next. DNA is the most fragile of the three, degrading on a predictable curve driven mostly by temperature. That hierarchy explains exactly what each site yielded. L-salt gave up molecules with no object attached because the fats outlasted everything they came from. Speed matters more than depth. The first hours after deposition determine almost everything, which is why a body dumped in cold, wet clay can outlast one placed carefully in a dry grave. Disgusting material survives disproportionately well because it tends to be fatty, it tends to be buried quickly, and nobody bothers to clean it up or curate it away. The conventional archaeological record is dominated by stone and pottery, and those survive because they are inert, not because they mattered most to the people who made them. Notice how these finds arrived. A road scheme in Blekinge, a tunnel project in Denmark, a university expansion in York, bank foundations in York again, peat cutting in Offaly. Rescue archaeology, not research design, is the engine of nearly this entire list. And every one of these objects was recovered decades before anyone could read it, then read later when chromatography, mass spectrometry, and sequencing caught up. The next major discovery of this kind is probably already excavated, boxed, and sitting on a museum shelf. Material has to survive the ground and then survive the archaeologists, and for a long time it did not. Calculus was scraped off teeth and binned as a standard part of preparing a skeleton for study. Coprolites were treated as curiosities, rather than data, well into the 1960s. Eric Callan, a Canadian botanist, effectively founded the analysis of ancient human feces in the 1950s, working out how to rehydrate desiccated specimens using a trisodium phosphate solution, a method still in use. He died in the field in 1970, and the discipline he started took decades to become respectable. Soft tissue was routinely set aside in favor of bone, partly because bone fitted the measuring and typological methods that already existed. Sonia O'Connor's discovery that museum stores held dozens of unrecognized preserved brains is a symptom of the same habit. What broke the pattern was information density. Once biomolecular methods matured, the gross material turned out to be worth more per gram than the artifacts. A stone tool tells you about technology. A stool tells you about diet, disease, migration, and local ecology simultaneously. A tooth's plaque tells you what a specific person ate, breathed, and worked with. The economics of research attention flipped, and with it, the staffing of departments. Paleoscatology, paleoproteomics, and biomolecular archaeology are specialisms that did not meaningfully exist a generation ago. Most of these techniques are destructive, consuming the sample to read it, which forces genuine decisions about whether to answer a question now or preserve material for better instruments later. Human remains research carries ethical obligations and consultation requirements that shape what can be sampled at all, and repatriation frameworks have changed how collections are managed. The Mumia trade sits at the far end of that spectrum as the clearest historical case of human remains treated purely as a commodity. The overall shift is easy to state. Archaeology stopped asking what an object is and started asking what it contains. Framed that way, disgust turns out to be a useful signal rather than an obstacle, because the more repellent the material, the more biological it usually is. The gains here are specific rather than decorative. Neanderthal diet was reclassified from near obligate carnivory to genuine omnivory, and in the process, a systematic blind spot in isotope analysis was exposed, since collagen preferentially records protein and effectively cannot see plants. Hunter-gatherer sedentism in southern Scandinavia was pushed thousands of years earlier, and storage economies were detached from agriculture as a necessary precondition. A complete human genome was shown to be recoverable with no skeletal remains present anywhere. The medical results are equally concrete. An individual's lactose tolerance was read directly rather than inferred from population models. Viral and bacterial carriage was documented in named prehistoric people, including Epstein-Barr virus and Streptococcus pneumonia in one Danish woman. Brucellosis was pushed back by centuries on direct molecular evidence. Antibiotic resistance genes were documented in mouths that predate antibiotics by hundreds of years. Oral microbiome diversity loss following industrialization was quantified against a deep historical baseline, and nearly 500 ancient gut microbial genomes were reconstructed from preserved stool, showing a richer microbial ecosystem than modern industrialized populations retain. Elsewhere, the gains are historical. Mummification chemistry moved from classical hearsay and 19th century assumption to measured recipes read off labeled jars, and in the process demonstrated trade in Southeast Asian resins reaching first millennium Egypt. Occupational evidence emerged from particles trapped in plaque, identifying a manuscript illuminator by the lapis lazuli in her teeth. Parasite loads were mapped across populations and migration routes. Dairy consumption was traced to individual people rather than to cooking pots. Pre-Clovis occupation of the Americas gained support from human DNA in Oregon Paleo feces. Preservation biology itself advanced, with protein aggregation now studied on a 2,000-year timescale in an actual human brain. The common thread running through all of it is that these are questions about ordinary life, and the durable record of stone and pottery cannot answer them. The limits are as instructive as the results. Ancient DNA degrades along a curve driven mostly by temperature, which means that in warm climates, most of prehistory is simply out of genomic reach. Tropical and subtropical regions are badly underrepresented in every archive discussed here, and Africa, where the deepest human history sits, preserves soft tissue worst of all. The result is a picture of prehistoric life skewed heavily toward cold, wet, northern Europe, which is an accident of chemistry rather than a fact about the past. Sample size is a second constraint. Lola is one woman. The Heslington man is one man. The York Coprolite is one meal cycle from one person. None of them can carry population-level claims on their own, however detailed the molecular portrait. Contamination remains the central methodological threat across all biomolecular work, and identification at species level is often contested, as the Brucella peptides show. Behavior is inferred rather than observed. A latrine area beside a hearth is an interpretation of a chemical gradient, not a photograph. Motive is further out of reach still, which is exactly why Bog Butter has 3 competing explanations after more than a century of finds and no sign of resolution. Some limits are self-imposed and appropriate. Destructive sampling means certain questions can only be asked once, and ethical obligations around human remains legitimately restrict what will ever be analyzed. Others are technical and may fall. Sedimentary ancient DNA is already recovering hominin presence from cave floor deposits with no bones present at all, applying the L-salt principle to genetics rather than lipids. Single molecule sequencing and better models of protein damage are extending the reach of both. The honest expectation is that a good portion of what has been described in this video will be revised within a decade. That instability is not a weakness in the field. It is what a discipline looks like when its instruments are improving faster than its archive is eroding. There is a reason this material feels different from a museum gallery of polished objects. Monuments record intention. Waste records reality. Every single find in this video was produced by somebody who had no expectation that it would ever be seen again. A tomb is a message aimed at the future. A chewed lump of birch pitch, spat out on a Danish shoreline, is not a message to anyone. Grave goods tell you what a society claimed to value. Dental plaque tells you what a specific person actually ate on an ordinary afternoon. The individuals who surface through this kind of evidence are unusually particular. A woman with gum disease and a recent meal of duck and hazelnuts. A man carrying whipworm through a crowded northern city. A decapitated man in a cold, wet pit whose brain refused to break down. These are precisely the people the durable record leaves out, because elites build monuments while everybody, without exception, eats, excretes, sheds, and eventually rots. The disgust, too, is ours rather than theirs. Fermenting 60,000 fish in a bark-lined trench was food engineering, and its descendants are still sold in Swedish supermarkets. Burying butter in a bog for a year was storage, or offering, or deliberate aging, and possibly all three. Grinding a mummy into medicine was, for several centuries, respectable European practice endorsed by physicians and paid for by a king. Aged cheese, cured meat, and fermented fish are the same chemistry maintained deliberately in kitchens today. The line between preservation and rot has always been drawn by culture rather than biology, which leaves the deepest irony in the discipline. What survives is not what mattered most to the people who left it. It is what nobody bothered to remove. The rest of it, the monuments and the metalwork and the carefully arranged graves, tells you what they wanted remembered. The waste, the plaque, the spit, and the fat tell you who they were. And somewhere in a sediment block from a rock shelter in eastern Spain, beside the cold remains of a fire that went out 50,000 years ago, that record is still sitting in the dirt, waiting for an instrument sensitive enough to read it.